What is up, most distinguished patrons of this channel? Today I have a special treat for you, and I know I've said that in a lot of videos, but today I got something that the cat drug in that you will not believe. So with that said, let's get into it. So I'm no stranger to questionable electrical wiring and janky electrical devices, but I found something that I had to share with you. And I'll give you a little backstory, quick backstory on this, make more sense. So I was contacted by someone and said, hey, would you be interested in this? And it happened to be a free welder. Now, nothing in this world is free, right? You're watching this video and you probably watched an ad. So, well, your time, you had to pay in your time to watch it. So nothing's free, right? But literally the ad was for a welder that was free and to anyone who wanted it. And well, of course I want it, as would you probably want it. And I got sent some pictures of it, and I wanted it even more after seeing the pictures, because I think I have found something that the world has never seen. And I almost guarantee you guys have never seen something like this, because I've never seen one, and I've been wrong before, but I don't think I'm wrong on this. So I have a special treat for you, and I'll go and grab it, set it on the table, and I'll let you bask in its glory, look it over, and think to yourself, what's so special about this welder? So you studied the pictures of it and you came back to the conclusion that, well, this guy talking right now is an idiot, and what's the big deal? It's a welder, right? And that's where you would be wrong, buddy. This is not just any welder. This is literally a homemade welder. Now, I know you're saying, well, how do you know it's homemade, for one? And well, I can tell you from the moment I saw this in a picture, I knew what I was dealing with. And we're going to go through this on a deep dive and look at it, and I think you will be under the same conclusion as I was, that this thing did not roll out of a factory somewhere. So let's take a look at the individual signs, I think, that this is a homemade welder. So right away, one of the things that jumps out on me, besides the hand-painted amperage letters, is the fact that this whole case on this sucker is made out of like masonite, like thin masonite at that. And I don't know about you, but I've never seen a welder that has all the exterior paneling made out of basically particle board. Doesn't make a whole lot of sense. It's definitely not durable. And I'll tell you what, if you accidentally ran into this sucker with something that broke through the side, you could get electrocuted pretty easy. So definitely not something I think Lincoln Electric or Miller would have engineered 20, 30, 40 years ago. So pretty interesting on that. Now this terminal block here, we still have the apprentice marks. Well, actually, not really apprentice marks, but whoever made this put centers on this for the terminals and, well, never polished them off. So again, I would say this is homemade. That's a great indication. Now, interesting enough, because this is an AC buzz box, much like an old Tombstone, there's no need to label polarity because it's both positive and negative. Equally balanced, 50-50. So what end you hook the stinger to and what you hook the ground to is of no consequence on this. Now, this material here seems to be almost like Bakelite or something. It's definitely older plastic, and it's not something that you would see on anything commercial. Also of note, all of the screws on this are flathead, and all of the nuts other than these are actually square nuts on the inside, which again, to me would date this thing being, I would say probably 1970s or older. I don't see this being built in the 80s, so this thing actually has some age to it. Now, the funniest thing, and what really told me this was homemade that I saw in the picture and I knew I had to have this thing, is the amperage chart. Now, I don't know what this white painted thing is. Maybe that was the guy's homemade welder brand, a backwards B or something. No idea on that. But it looks like they took a pocket knife and etched the masonite with a little line and a ring. It probably doesn't come out too good on the video, but there's like a ring there, and then they used whiteout more or less and then marked low, and then all of the amperages. High is above, I think that's 180, so maybe 190 to 200, 160, 140, 20, 100, 80, 60, like that's 60 by the look of it, but then this looks like 90, and that says 20, so I don't know what's going on here. That's quite an interesting, range there. And we're going to look at how this works and the mechanics of this in a little bit, but that's pretty interesting. I'm not really sure how accurate that is, but guess what, guys? We're going to test that and see if it's even close to accurate. Like every homemade barn find welder you run across, it comes with a whole bunch of spider eggs on it, loose cord ends, because why wouldn't you have that tight? It doesn't matter, right? Because it's janky anyways. Has an older 240 volt plug, which I don't happen to have an outlet like that, so I'm going to have to convert this plug to something a little bit, well, I don't want to say safer, because I don't think this thing is really that safe anyways, but that's interesting. And also, every backyard barn find welder has, of course, cuts in the cord. I'm going to have to investigate that a little bit before we go and plug this in. This channel might be known as making mistakes, but you got to be smart, Like I always say, if you're going to be an idiot, at least be smart about it. And as you can see, particle board side panels that are already, who knows, chewed away by mice or kicked in. And then there's also particle board that part of the transformer is sitting on to isolate it by the look of it. So pretty interesting. In case you're wondering how you adjust amperage, this crank handle on the top adjusts a shunt in the transformer and raises and lowers it in order to change the output of this machine. And I'll explain how that works in a minute. But I gotta say, this works a lot smoother and a lot better than most of the welders I've used that were vintage like this. I mean, this was common with the Miller Thunderbolt. I'm not sure that Lincoln ever used this setup, but Miller did, and a lot of other manufacturers used a crank handle on the top of the machine. And as you crank this up and down, that indicator rod on the front of the panel will rise and lower, indicating output amperage. So here's the meat of the operation back here, and this is how I received it. It did not have a back panel. It probably was masonite, I would assume, because these live terminals, or well, it'd be live if it was plugged in the wall, but I'm not an idiot, are so close to the back panel that if it was metal and someone bumped it, you'd go for a free ride on the Lightning, no doubt. Now the frame itself that this welder's made out of appears to be made from, like, I don't know, maybe a bed frame or something. And the welds on it are pretty scabby, which doesn't give me too much faith that they knew what they were doing when they wired this transformer in. So I'm definitely going to take a good look over this and make sure that it's wired properly to at least probably function. Now, of interesting non-electrical code conformance, the little cord end clamp is in the masonite there, and I don't know what that's doing. I guess that's so you can't pull the cord out any further than what it is, because that would be bad. You'd pull these out and you'd have loose wires. Now, the back panel did not come with it. It's missing. I hope that they were smart enough not to make it out of steel, because these terminals, which would be live if this was plugged in the wall, if you were to bump that back panel, you would bump it literally right onto these and cause a short. So My guess is, again, that that was wood. But the overall build construction definitely raises a lot of questions as to, well, they weren't much of a welder, so hopefully they were a decent electrician, but I don't think they were that either. Now, where things get interesting is the fact that this transformer is painted red. Now, I do see evidence that this was painted in this metal frame. It was not painted with the sides on because there's no red paint on it. But this wheel over here has a bunch of red paint on the side, as does the other one, which makes me believe that whoever put this in here and assembled it basically welded this transformer to the frame, or the frame is more or less welded to the transformer, and then they painted the transformer red in place. Now, I say that because red transformers are universally what you would find inside Lincoln Electric machines, like the Ideal Arc 250. The whole inside was painted red from the factory. Now, I know without a shadow of a doubt that this is not a Lincoln Ideal Arc 250's transformer. I've torn apart more than a few of those machines, and this is definitely not. This is not a transformer out of a tombstone. This is an absolute gigantic transformer that I don't think would be in anything less than a 250 amp class, if not bigger, welder. Which is kind of odd that that would be in this size of machine. Now, you can see this doesn't actually take up more than about half of the case. The rest of it's dead space, more or less, for that amperage indicator that's up here. But this is realistically, even for the day that this was probably built, way oversized for a 200 amp welder. Now, very few welder companies use a top crank handle adjustment for the transformer welder. Miller made the Thunderbolt. Like I said, there were a bunch of generic ones out there that did. And my thought initially was that, well, this is a Lincoln Electric transformer, and I simply don't think that's the case because I'm not aware that Lincoln ever made a top crank handle. And this sucker being so big, I just don't see it in any kind of conventional, like more heavy duty stick welder. So I believe, and I could be wrong, if you've seen this setup in any welder ever, make sure you leave it in the comments so we all learn from you. But I've never seen something like this transformer in a welder before, so I believe that this is unique, and I don't believe it's homemade. They likely took this from something else, so if you know what that something else was, again, leave it in the comments. So anyways, that power cord comes into this Bakelite or whatever plastic junction box, we'll call it, or junction plate, and they have the ground hooked to here, and it looks like they use their kids' erector set nuts to make this, and that more or less hooks up to the ground. And then the two hot leads from your 240 volt, one goes here, one goes here. Well, at least that's not loose, thought it was. And then that goes to the primary coil of the transformer. Let's look at that. So interestingly enough, the crank handle on the top of this more or less spins and raises and lowers this into the transformer. And I'm no electrical engineer, so take this with a grain of salt, but what this is I believe they call it a shunt, and that shunt basically lowers and raises and changes the magnetic permeability between the primary and the secondary windings. And let's do a little quick book learning on that just because. So I've talked about how transformers work in a bunch of other videos, and I'm not going to go too in depth in this video, but I'll put a link in the description to a video where I broke down how a Lincoln Tombstone welder works. I'd highly recommend you watch that to understand more of what's going on here. Now back to this device in particular, it's a little bit different in how it adjusts amperage than like a Lincoln Tombstone or a Dial Arc. This is actually very similar to how an Ideal Arc 250 Lincoln works, and it's kind of a unique idea that they came up with to adjust amperage. So what we have depicted here, the gray is the primary winding. This is what's hooked to your wall outlet power. And the red winding is the welding output on the front of the machine. Those coils of wires are wrapped around a core of, in this case, laminated steel. Now the core is normally closed. So it would be more or less like cutout laminations and then the wires wrapped around them. Well, on this device, it appears as though the core itself is split and a wedge, I'll draw it right here, with a crank handle bolt lowers a wedge in and out of the split in this core, and what that does is it changes the, I guess the term maybe would be magnetic permeability of the core. Now, as AC voltage is hooked to this primary coil here and it's pulsing positive and negative, the fact that this coil is in close proximity to the output coil is enough to where there will be some change in electrons in this, but it's not very efficient on its own, and that's the purpose of winding this around a core, because the core itself more or less acts as a more efficient way to transfer that pulsing, that positive negative voltage, that energy into the secondary coil. Now, a traditional welder, like say a Dial Art 250 or even a Lincoln Tombstone, has a solid one-piece core, or well, it's laminated, but there's no break in it. This, having that break, means that there's very poor transmission of the positive negative from the primary to the secondary through electromagnetism, but that's the point of the shunt. I believe they call it a shunt, and it's likely tapered in a manner to where the further in it goes, the more permeable it is to magnetism. So it's probably shaped something more like this. And when you adjust amperage by pulling it out, the transmission primary to secondary is very poor, and as you crank it down, it becomes much better. Therefore, due to the winding ratio, which is fixed, you can get more output. So more or less a way to look at this shunt setup that this uses is a way just to screw with the efficiency of primary to secondary transfer, which is, again, a lot different than a lot of other welders out there, and it shares nothing in common with like a more modern welder. Even those still have transformers, but they control them with computer chips and MOSFETs and all sorts of fun stuff. But this is an old school way of making more or less a variable winding transformer or a variable output transformer without using the Lincoln Tombstone method, where you more or less just tap off at different points of the coil on the secondary to get different outputs. This gives you a lot more variation. The downside to this setup is that its efficiency has got to be down in the gutter, to be honest, and we'll test that in this video. And not only that, I don't anticipate that this type of a transformer is going to have any kind of reasonable efficiency. More or less, as that AC current is pulsing on the primary side, my guess is it's just going to generate a massive amount of heat, and this thing is probably going to be at best 30–40% efficient at turning input power into output power at low outputs. Its efficiency probably will actually rise as you get closer to max output, but at lower outputs, this thing is going to be pretty terrible. And I don't even know how much output I'm going to get since I'm running it on a generator. My guess is I won't even hit 60, 70, probably no more than 80, 85 amps with this sucker before the breaker trips, the 30 amp breaker. So right here is that shunt I was talking about that I believe is just changing how much the magnetic flux between the primary and secondary is more or less transferring. And as you crank it, one way it comes up, the other way it goes down. So pretty simple setup. And like I said, I believe this transformer is probably not out of a welder and it came out of something else, but I could be wrong. Feel free to leave a comment if you know, like I said, where this bastard came from. So I'm going to show you a quick little test that you can do on some kind of old machine like this to determine if it's at least safe to plug in a wall. I have a standard volt ohm meter here and it's set for resistance. And when I touch these two wires together, Read 0 ohms of resistance, and I have it audible so you can hear it as well. More or less, there's a direct short between those 2 points, which there is, and it's telling us that. What we need to test is the first thing I'm going to do is I'm going to put it on the ground wire. This is green. That should on the plug go to the green ground, and I'm going to test that here. So now that I have the plug up here, I'm going to check the ground plug, which is this guy right here. And I do have continuity between the ground plug and this. That's good. I'm going to check if I have continuity between the ground and either hot wire. That one I don't. And that I don't. That's a good sign. That's giving an indication that at least neither one of these inside of the cord is shorted to the ground wire, and the ground is indeed hooked up to the right terminal, which also means that it is wired correctly. Now, the main thing that I'm concerned with in here is that this ground wire is not actually hooked in any manner to either of the hot wires that are on here. And I'm going to show you here. First thing I'm going to do is touch, and you can see this being grounded to the core of the transformer. It has continuity there. It probably has continuity over here. Paint's a little rough, and that would make sense. Most welders, the case is grounded to the ground plug, so that's all normal. That's done that way so that if your wire, for whatever reason, shorts out, that it will trip the breaker because it gives it a path back through the ground wire to cause a short, more or less a high amperage drain on the breaker, so it trips. Anyways, we now want to confirm from the ground lug to the hot wire that we do not have continuity, and we do not. I do not hear it or see any reading. That's one wire of the 240 volt. Here is the second wire. So both hot wires coming into this transformer are not shorted to ground. That's a great sign. Now you guys got to remember that this hot wire, both of them that come in and power the primary coil on this transformer, that coil can over time short out to this core. Even though that's wire wrapped around the core on the primary, it's actually jacketed in some form. It could be a coating on a wire or cloth wrapped, whatever it is, that is electrically isolated from this core. And if there is a short in it at all to ground, we would see continuity between like this case and the hot wire, and we do not. So that's a great sign. Now I'm going to go in the front of the welder and test that the outputs are not shorted to ground either. Okay, I got it hooked up to one terminal on the front. Got no reading, that's great. Hooked on the other terminal and no reading. All of that shows me that this thing's reasonably safe to plug into the wall. Nothing is shorted out to the case, and the transformer itself is not shorted out to the core either, so that is a great sign. The last thing I'm going to do is I'm going to check between the primary and secondary windings and verify that there's no electrical continuity between those. And reading both terminals, nothing. So as far as I can tell, everything's perfectly fine with this sucker, so I'm going to change the plug end and we're going to hook it up and try and do some test welds with it. So I got the new cord end on this sucker, and man, this cable is a bit overkill for this thing. It's like 6-gauge wire. Anyways, I also got the quick connects installed, and I was sitting here thinking, I can't believe I didn't notice this earlier, but there's no off switch on this. So as soon as you plug this sucker in, that transformer's live, and I guess you're going to be welding something. And is that a deal breaker? No, but you know, honestly, they put an off switch on an electric chair, so I don't know, it's kind of an important thing to have. So minor oversight on the engineer that built this. So anyways, now that this thing's kind of set up, what I'm going to do is plug it in, and well, plug it in with the breaker off so I'm nowhere near this, flip the switch and make sure that the breaker holds. I have it on almost the lowest it'll go, and I guess we'll see what happens. Well, this sucker's got quite a little rattle to it. The laminations in that transformer probably aren't tight anymore, and it has a little bit of shimmy in it due to all the angry pixies rolling around in it. But anyways, it's only pulling about 1.3 amps at idle with no load on it. So as far as I can tell, everything's looking pretty good. There really isn't any kind of short that would be concerning. So that's all looking good. The power factor at idle is 0.22, so pretty atrocious as I would have expected. And this has no obvious power factor correction, no capacitors. I mean, this thing is as simple as you can get. It's a literal transformer out of something that someone repurposed for welding. So we're clear as mud here. This guy right here, we're metering the AC amperage on the output of the machine. This is measuring the output voltage, and once I strike an arc, it will drop to what the rod requires to keep an arc lit, which should be around 20 to 24 volts. And then up here in this little guy, we have our current draw, which is the actual consumption of it. However, the actual current loading on the input line would be much higher than that because the power factor of this is so poor. And that's why the wattage, which is depicted here, will be a lot higher than what the current draw would suggest based on our 250 volt line voltage. Anyways, that should cover what you need to know. So anyways, I'm gonna go strike up an arc and run it for probably, I'll do 2 beads, watch the footage myself, and then we're gonna come back and talk about what I found. All right, so I just got done reviewing the footage and coming to an understanding of the data, and I'm going to go through it with you guys so you're on the same page as me. So the first thing I'll say is this sucker is not efficient at all, but I didn't expect it to be. Purely transformer welders just simply aren't. They can't hold a candle to modern equipment. But speaking of inefficiencies, so its power factor is 0.45. That is, in a nutshell, typical for a transformer machine, but very poor if you attempt to run this on a generator. And I'll explain a little bit more about that in a second. But a modern machine with power factor correction can achieve 0.99, 0.98 under load. Now keep in mind, I ran this at a pretty low output. Had I cranked up the output, the power factor may have increased. And all this is really talking about is it's basically spitting back reactive power towards the generator, in my case, or your wall outlet. So what that means in a nutshell is it's spitting reactive power back to your electrical panel, or in my case, my generator. And that's not a good thing because, well, at a 80, 90 amp output on this machine, it's loading the input line to 30 amps. That's what the breaker would be seeing, which means to get any kind of output on this machine, you'd need a 50 amp, 240 volt breaker, versus a modern machine could achieve more than 200 amps on less than 30 amp breakers. So basically you just need really big power wire and a very large breaker to get any output out of this. Power factor is especially important on generators where a poor power factor is just going to cause breaker trips, even though the device actually doesn't need the amount of power that the breaker's seeing. Anyways, primary side, we're looking at 7,000 watts is what the loading was on the input side. Keep in mind, that's including the reactive power. The actual loading that the device consumed, so only consumption of the device, was 22 amps at 240 volts. That's what it dropped down to while it was operating. So it's 5,280 watts is actually consumed to weld this 6013 rod that I did. That is a ton of power. Now, to put in perspective, 22 amps is what it's actually consuming. The breaker's going to actually see 29 amps. And I'll tell you what, my generator breaker trips at about 31 amps. So where it was set at is about the most that I could actually get out of this before I would likely suffer a breaker trip. Now, the output of the machine, the rod ran at an average of 24 volts. And the output, according to my meter, was 82 amps. Now, I believe I said it was somewhere around 70 looking at the beads, and I would tend to believe my beads on this plate more so than that meter. That meter tends to read about 5 amps high. So let's just say somewhere between 70 and 82 amps is what it was outputting. Well, at 82 amps, 24 volts, the output of the machine was 1,968 watts, which is not a whole lot given how much input power was given to it. And to put it in very simple terms, the efficiency of this device is basically 37%, which means at this output, which is somewhere between, say, 75 and 85 actual amps, it is only 37% efficient at taking that input power and turning it into output power, which is probably the worst I've ever seen on a welder. I don't remember if I tested the Lincoln Tombstone or not, but my guess is that could at least achieve 42, 43%. Basically, this thing could be a portable heater, and my guess is if you did a bunch of welding with it at the output I have, that transformer would likely get pretty hot. So anyways, let's go to conclusion. So what did we learn today? Well, we learned that janky homemade welders can in fact weld, and one of the things I kind of got a real good laugh at is when I cleaned up here and came over here and looked, I forgot I never even told you guys what the setting was. So this is 80, 60, 40. It looked like 90, but it's 40, 20. It's somewhere between 20, we'll say 30 amps. And it was actually outputting somewhere between 70 and 80. So clearly this is off, which might be a good thing. Maybe if I crank it all the way up to 180, it's more like 300, and we have a 300 amp welder here. But unfortunately, I can't test that because any more than where it's at, and it's just going to trip the breaker that powers this. If you guys are interested in seeing what its maximum output is and how efficient it is, let me know. Maybe I'll find a way to get this to my buddy's house, hook it up to an actual 50 amp breaker, and set it to max and see what it'll do. I'm kind of afraid of that. I almost think something's going to catch fire on this, but hey, who knows on that. But the great thing with this is that I actually wanted to build a transformer for you guys to show you how it worked better. And this, I think, is really about the best example I could come up with, and because it's laid out exactly how I would have done it if I was going to make a homemade transformer. Now, I really don't believe the transformer in this is a homemade job. It's wound too nicely. So clearly it came out of something, maybe another welder, who knows. But the technology in this is about as old school as you can possibly get, and the funny thing is it still works. Now, would I give up any kind of modern welder for this? Absolutely not. However, this is kind of a testament to people's ingenuity, and who knows, you know, a free transformer and $20 a masonite and you have a welder, that beats, you know, when you're poor or don't have any money for something, beats having no welder. And I really enjoy that kind of ingenuity and that effort, because it's all about getting stuff done even when you don't have the best equipment. And I'll tell you what, I wish I had a little bit more of a backstory on this as to where it came from. The elderly lady that ended up giving it to me didn't know much about it, but the guy whose garage she was cleaning out had a ton of like old Model T parts and flathead parts. So, I mean, this thing's been around the block, and I'm sure that the guy used it. I mean, you don't spend this much time building something like this not to use it. So I'm sure that, you know, this was building stuff for many years before it kind of just got lost in the corner of a garage. And by the way, shout out to the lady who gave me this. I told her what I was going to do with it, as in I made YouTube videos and I would share this with the world and the internet. So give that lady a shout out And a thanks in case she actually watches this video. I'm going to send her a link to it. Thanks to her, she made this video possible. So anyways, with that said, thumbs up to her for helping us out. And until next time, take care.